So do you see my presentation? Okay. Okay, thank you. Okay, so good afternoon, everyone. First of all, I'd like to thank the organizers of ISM 2023 for the beautiful work done throughout this period from phase 1 till now, and for giving me also this opportunity to give this talk today. A special thanks is for our coordinator, Shane, for the beautiful discussions that we did throughout these months. Okay, so my presentation will be on two-scale convergence of thermoelasticity. So two-scale convergence is a special method from the class of homogenization. So the plan that I will follow throughout this talk is the following. First, I will start with homogenization, in which I will explain why people are interested to homogenization in two perspectives, in a physical perspective and a mathematical one. Then I will recall some results from thermoelasticity, since Iman has had already talked about thermoelasticity. After that, I will pose the problem. Sorry, I will describe the main problem of this talk to arrive to the method of two-scale convergence, and then I will close my talk with some open problems. Okay, so let's start by a motivation. So this is a picture of what we call composite material. So what is a composite material? A composite material, let's take an example. Imagine that you want to make an object from a pure material. For example, let's consider a type of 24-karat gold. So you consider pure gold and you want to make some ornaments or some wire or something like that. Unfortunately, if you make such object, it will break. It will break very quickly and very easily. So you need to mix this pure material with another one in order to change the property of your initial material. Okay. So for example, we mix pure gold with silver or copper. So once you mix both the materials, you get a new one. Okay. You get a new one. And this new one, it can be considered as a heterogeneous domain. Okay, so it can be this first picture. And if you want to improve the quality of your material, so here I consider that once I mix both the materials, I get something uniform. Okay, something periodic. But in general, it is not uniform. It can be non-uniform, non-periodic. But for our convenience, I consider the case of periodic distribution or periodic mixing. Okay. So in order to get a strong material, you have to increase the denominator of ratio, or you decrease your ratio epsilon. So once you decrease your epsilon, so we observe that step by step you get something in which you don't see neither copper nor pure gold. So you get something which we call composite material. So another example can be from aircraft industry. So in aircraft industry, if you want to make the body of a plane, if you consider pure material, it will be heavy. So what is the solution? You have to consider a body, a structure, a material which is lightweight but strong. It may seem contradictory, but with the theory of composite, it is possible, and even mathematically it is possible. So the question in homogenization is about asymptotic behavior. So what is homogenization? We call it also averaging, because when you mix materials, you are looking for the best averaging, the best limit, the best homogenized composite, the best homogenized material. So homogenization is about the study of microscopic or bulk behavior of solutions to PDEs or other type of equations posed on a heterogeneous domain or media where the heterogeneities are present at the microscopic scale epsilon. So the heterogeneities can be in the form of, So the heterogeneities can be in the form of fine mixing of two or more materials with different physical properties in the domain, or due to singularities in the domain in the form of pores, granules, etc. So the nature of typical problem in homogenization is the problem. So the problem is posed on the heterogeneous domain. We assume that it has a unique solution, since we are looking for the best composite material, lightweight and strong. So it must be unique, a unique result. So we assume that the family of homogenization problems are unique, and also we have that heterogeneities cause the solution to develop high frequency oscillations, because when you couple between these materials, you have some heterogeneities, and these heterogeneities may cause some irregularity in the solution. So if we want to consider numerical analysis, we have to pay attention, because sometimes it can be so difficult to get the behavior, the bulk behavior, or the oscillations in the solution which are already at a microscopic level. Okay, so these oscillations that translate in somehow the heterogeneities that exist between the materials can be models like a coefficient which is periodic. For example, here I consider the sinus x. So if you consider the sinus x, it is a beautiful function which is regular. And once you increase the entry of the sinus, for example, sinus 4x or sinus 10x or sinus 40x, we observe that the wave sinus start oscillating so quickly, okay? And this oscillations cause an irregularity in the form of the solution, okay? So these pictures can give you an idea about how our solution will be depending, or will depend on the coefficients which are oscillating. So what is the way out? So we have to, what do we have to do? So do an asymptotic analysis as epsilon goes to 0. That is what we do in general. So it is, we try to approximate the solution U epsilon corresponding to the heterogeneous domain for small epsilon strictly positive by the solution of a homogenized problem in which the small parameter does not appear. Okay, and we will see further that the norm in the epsilon norm of our solutions are equivalent to the classical norm without epsilon. So it will be better to have an idea about the limit problem, the homogenized problem, then deduce some qualitative and qualitative properties about the original one. So the mathematical problem is the following. So we have to identify the homogenized equation, which is not, which is just the limit problem, to prove the convergence of U epsilon corresponding to the heterogeneous equation to that of the homogenized equation as epsilon goes to 0. We have to capture the oscillations in U epsilon. So this is done in general due to correctors, okay? And the solution together with the correctors can be used to get good approximation to the original solution. Okay, so to summarize, mathematically speaking, we consider a family of Cauchy problem, which depends on epsilon. For each epsilon, we have a Cauchy problem. And we assume that this family of Cauchy problems is well posed, okay? And if Z epsilon, if the solution of this family converged to Z0 in a certain topology, then we are interested about this limit of the family of Cauchy problem, which is just this one, okay? But how to show that Z epsilon converge to Z0? So this is one of the questions that we're gonna be interested in this talk. Okay, so let's start by a BB example. Okay, so the BB examples that we can, the BB's examples that we can consider in general, they are elliptic examples. So here I consider a problem that models the transfer or the conductivity, the thermal conductivity in a certain material. So we have a material, a heterogeneous material, which is just the coupling between different materials, a material of type 1, another of type 2, etc. And we want to have some qualitative properties about this problem. So as usual, we have some assumptions. So I assume that my coefficients are periodic, okay? And that A epsilon is one periodic function, with positive and which is positive and differentiable. And since we are considering a periodic structure at a microscopic scale, like in composite materials, then epsilon will be very small, causing rapid oscillations in the coefficients and hence in the solutions. Okay, so what is the homogenized equation? So there are some difficulties that we encounter once we talk about convergence for such kind of problems. So it can be seen that the periodic function. So since E epsilon is periodic, so it will converge weakly to the mean of this function. So E epsilon converges to the mean of A. And further, we can show that due to some standard variational formulation, that U epsilon also can weakly converge to U in H1 0. But what is the homogenized equation or the average equation, the limit equation? Does the homogenized equation is just this equation, this limit equation that satisfies where U satisfies this hyperbolic equation? So unfortunately, the answer is no. So the limit problem is something that is not that cannot be expected. But for example, for an engineer, if you ask him what is the limit of this problem, he can tell you that it will be a problem which is elliptic, but this time with a mean that will be constant. Then I will obtain just a multiplicative Laplacian. Okay, but unfortunately, it is not the case. We obtain a limit problem which has this form, which is minus d over dx of the inverse of the mean of the inverse. Okay, so we have a Laplacian multiplies with the inverse of the mean of the inverse. So another question, another interesting question: what about the n dimension? If I consider the same problem, but this time in an n-dimensional case, can we say that we have just to replace A with a matrix, then get the same homogenized or limit problem? Unfortunately, the answer also here is no. We cannot replace small a by a matrix then and conclude. And fortunately also, because otherwise we're gonna be jobless. So a homogenization gives us the chance to work on challenging problems. So the difficulty in general is that weak convergence does not preserve these non-linearities retained by the coefficients. Okay, so in particular, when we have studied strong convergence, if En converge to A and Bn converge to B, then we conclude automatically that the product converges to the product. But for a weak convergence, the situation is different. So if we have two sequences that weakly converge to two limits, we cannot deduce that the product converge to the product. You can just think about these examples. Considering the sinus of 2p and x weakly converge to 0, but the square converge to 1/2. Okay. So moreover, this 0 and this 1/2 does not tell you did not tell you any information about the structure or the character of the sequence. Okay, so here you start with a sinusoidal sequence, but once you make the weak convergence, you lose this character of the sinus wave. Okay, so this motivates us to consider other type of conversions, other type of topologies. Among the methods and of problems that we can find multi-scale asymptotic expansion method used by several authors like Binsu and Leon Zhao, and Twoscale method, which is the object of our presentation, and there are other types of convergence like G convergence, gamma convergence, and H convergence. So now what I will do, I will consider the homogenization problem, the family of homogenization problem and the limit problem, and I will take A of y as a periodic function, oscillating function, and I will draw both the solution. I will draw the sum of u epsilon and the solution u0 and see what happens. Okay, so if you draw both the solutions, so you're gonna observe that the solution is just the curve with blue in blue line. Okay, and the solution u epsilon is the oscillating is just the oscillating function or the oscillating solution. Okay, so this u epsilon retains and remembers the character that contains its coefficients. Okay, so the character, the structure, and the character of the coefficients appears in the solution, in the profile of solution of u epsilon. Okay, so here I consider f equals the unity and ay is just this is one thing. So now I will go over thermoelasticity. We have just seen with Iman what is thermoelasticity. So here I recall quality and stresses. So, as an example, consider a rod, okay, that we heat with a source of temperature, and when we heat it, we observe some deformation, okay, and these deformations are modeled by a wave equation, and since we have used heat in order to get this deformation, we have here a heat equation. So there is in somehow a duality between wave equation and heat equation. So this is what we call thermoelasticity. But in order to show this generation of wave, this generation of wave and heat, we have to couple these two equations. So before coupling these two equations, I have to say something about wave and heat. So we already know that wave equation has a conservative energy. It is a Hamiltonian equation, and the heat equation has an exponential behavior. So among interesting questions, what character we're gonna inherit if we couple between both these equations? Okay, are we going to inherit conservative character, exponential character, or something in between? So this is depending on the type of coupling that we are considering. Okay, so here I couple the equation. So strong coupling is just, so this is something that Iman has just said before. So strong coupling is just the system and weak coupling is the other one. Okay, and the energy associated to the coupling system is given like this, okay? And there are several literature, several works on this direction. For example, for strength coupling, I can say that the energy decays exponentially to the equilibrium, and for the weak coupling, the energy changed totally the behavior. It decays polynomially to the equilibrium. Okay, so this is just a remark. So now I arrived to the problem, the heart of this presentation. So some annotation I consider here omega as a bounded domain with boundary the omega. Y is the periodicity cell. A hash is just the symbol that denotes the Y periodic functions. C0 infinity of omega is the set of test functions. C hash infinity of Y is just the set of C infinity functions on Y, which are Y periodic, and LP hash of Y is defined like this, and so on. Okay, each one hash is the completion of the C infinity hash of Y, and each minus one hash is just the joule of each one hash. Okay, so this is our problem. So here I consider this problem, this coupling problem, this family of coupling problem, which depends on epsilon. I consider several coefficients which are functions, okay, in order to see what happens when epsilon goes to 0. So I'm interested to see what happens to each coefficient next to the operators, okay. And the energy is just a transformation of the previous one, okay. It's just a transformation of the previous one, and I have some hypotheses. So the classical hypothesis that we put in general is the following: A and B are assumed to be self-adjoint Y periodic matrices satisfying this property or estimate on of elasticity and boundedness, and I assume also that C, D, and Y are bounded positive. Okay, so by noting A epsilon equals minus div A grad and B epsilon minus div B grad, I can consider this inner product defined in this way, and the induced norm is the following. Okay, the epsilon norm that I noted as epsilon norm is just this norm. Okay, so of course the energy of our system is just 1/2 times this norm. Okay, and the state space is h1 0 times L2 times L2. So here a remark: we can show, according to the hypothesis, that each norm is equivalent to the epsilon norm. Okay, so if we get informations, asymptotic behavior on the each norm, we can deduce what happens for the epsilon norm and vice versa. Okay, so as usual, we have to verify that our problem is well posed. So I write my problem as a Cauchy problem. Okay, I write my problem as a Cauchy problem. U prime equals A epsilon, bold A, capital A, U epsilon, and here is my operator A epsilon with domain defined in this way, and A epsilon U is in this way. And we can show that A epsilon generates a family of contraction semigroups T epsilon on the state space capital H. Okay, so the proof is just based on Lumer-Phillips theorem. We show dissipativeness due to the inner product, okay, that I defined before, due to through this inner product, and I show that 0 belongs to the resultant set of A epsilon. Okay, so now I give a result about a priori estimates. Okay, so this result about a priori estimate give us some information about our solutions, U epsilon, theta epsilon, and also about A 1/2 grad U epsilon and B 1/2 grad theta epsilon. So it tells us that each component is L2 bounded uniformly with respect to epsilon. Okay, so and this is a very important result. So I give a sketch on the proof of this result. I start with the resultant equation. Okay, so this resultant equation will give me a family of three differential equations. Okay, and once I write V epsilon as lambda U epsilon minus F, I replace it in the last two equations, and I get these equations. And since I have this coupling parameter here, gamma epsilon theta epsilon and gamma epsilon u epsilon lambda, I multiply here by lambda u epsilon and the second one by theta epsilon, and in order to absorb this coupling parameter. Okay, and I get this equation. So using the hypothesis before and Young's inequality, I get this last estimate. Okay, and this last estimate is true whatever for all lambda positive. Okay, so consider lambda equals 1 or just minusing this, you're gonna get the required estimates. Okay. Okay, so now I will introduce some functional spaces that we call the Joule space of admissible microscopic fluxes of tensor fields on Y, WA. So WA is just the state of psi in L2 hash of Y to the power n, such that the divergence on Y of this function is 0 in the distribution space H-1 hash, and WB is the same space, but we change A by B. Okay, so this space is for treating the wave equation, and the second one to treat the heat equation, since this is just the conductivity operators or matrices in the coupling problem. Okay, so now I arrive to two-scale convergence. Okay, so two-scale convergence is a method that has been introduced by Ngeetsing in 1989 and then developed by Grégoire Allaire, and after that refined by other scientific people like Shikov and others. So we say that a sequence U epsilon which is bounded in L2 is weakly two-scale convergence to U0 in L2 of omega times Y, and we'll write U epsilon two-scale converge to U0 if we have this expression, okay, or this limit. Okay, the limit when epsilon goes to 0 of the integral over omega of U epsilon phi B equals the integral of omega cross Y of this expression. Okay, and this is true for any phi in the set of test function and B in C infinity hash of Y. Okay, so this is a strong version of scale convergence. So we say that U epsilon, which is bound in L2, is strongly, this time is strongly two-scale convergent if we have that this limit is verified for all functions V epsilon, which are weakly two-scale converge to V of xy. Okay, so here I give some remark. If you replace B by 1, then two-scale convergence is just weak convergence. So you get weak convergence by replacing B by 1 in the previous definition. Okay, so you replace B by 1, and you get that we have the integral of U epsilon phi equals this, and we have that phi is in the test function, and by density you can return to L2. Okay. The second remark is strong two-scale convergence implies weak two-scale convergence. So again, you consider V equals to the product of phi and B, and phi and B two-scale converge to phi x B of Y, and you get the right implication. So in order to show that our operator E epsilon converge to a certain limit operator, we used the weak two-scale Trotter-Cato theorem. Okay, so two-scale Trotter-Cato theorem tells us that if you have a family of semigroup T epsilon generated by E epsilon, such that the resolvent two-scale converge to a certain operator, pseudo-resolvent, call it pseudo-resolvent, and that the range of this pseudo-resolvent is dense in H, then E0 is the generator of T0 of T. There exists an E0 which is the generator of T0, and this pseudo-resolvent is no more but the resolvent of the homogenized, the limit problem, and you have moreover that the semigroup family of semigroup converge to the limit semigroup.
So
Okay, so
just,
so here is
sorry, Salim, just to mention, maybe only 4 minutes left maximum, or else there'll be no time for questions.
okay. So you give me 4 minutes.
I think so, maximum, very maximum.
Okay, okay, thank you. Okay, so now we arrive to this theorem, which tells us where our solutions converge. It will be very helpful in answering our limit. So there exists, we can show that there exists U0 theta 0, okay, in L2 of omega, and Xi0 and Xi 0 in L2 of omega WB and here WA, such that we have these conversions, two-scale conversions, okay. So another result, so there exists a unique function up to an additive constant U1 in L2 of omega H1 hash that solves the cell problem, the following cell problem, such that this C0, which is just the limit of E1 half grad U epsilon, is no more but this combination, okay? Combination, it is just the sum of the gradient of XU0 and gradient Y U1 multiplied by one half. And same thing can be said about the temperature component. Okay, so as a sketch on the proof of this last result, so we have that we have just to show that Xi0 minus square root of A grad XU0 is perpendicular to L2 of omega WA by variational methods. Okay, and you can use also by using generalized Wheel's decomposition lemma, which is just this lemma, which says that if eta is in L2 of Y and in the orthogonal of W, then we are sure that there exists a U1 in L2 of omega H1 hash, such that eta of Y is just the square root of A grad Y U1. Okay, and somehow it says that the orthogonal of divergence-free functions are just the gradients. Okay, so this is another way of reading the Wheel's generalized Wheel's decomposition. Okay, so the last theorem that gives us this limit operator is stated here. So we have started from a family of semigroup T epsilon generated by E epsilon, okay? And we have used True-Tarkato theorem, the weak version of True-Tarkato theorem, in order to get this convergence of the family T epsilon to T0. And the resulting operator E0 is just this operator. Okay, so here this symbol is just to say it means the mean of these functions. Okay, so it is -1 over the mean of C and minus the mean of gamma over the mean of C. Of course, I can consider gamma, C, and all these parameters equals 1, but I want to see what happens to these coefficients, since the mean of a fraction is not the fraction of the mean. So it is, for me, it is as a first project, interesting to see what happens for these coefficients when epsilon appear at infinity. Okay, so I conclude rapidly in 1 minute. I'm open. So I have traced this of equation that we have observed kind of questions. What about non-periodic case? Okay, and what about considering schemes of such coupling problems and showing uniformly estimates with respect to H and epsilon? And what about also considering nonlinear case and looking for any attractors that will appear in our study? Okay, so here are the references that we are considering throughout this project, and thank you for your attention. So sorry for the delay. Thank you.